In this BocaPhysics video, you'll see a set of simulations depicting the behavior of electromagnetic waves at the interface between two linear but non-magnetic media. We're interested in the reflection and refraction of an incident wave. Let's suppose we have linear media characterized by indices of refraction n1 and n2 respectively. We take the normal to the interface as pointing to the right from this viewpoint. Next, we see an incident wave Ki that is at angle theta I with respect to the normal. These two vectors define the plane of incidence. The normal to the plane of incidence is perpendicular to this plane in which both vectors lie.
The four boundary conditions are: the normal component of the displacement is continuous, the normal component of the magnetic field is continuous, the tangential component of the electric field is continuous, and the tangential component of the H field is continuous. These four boundary conditions must hold on the interface everywhere and for all time. Therefore, the dot product of the incident wave vector with some vector r is equal to the dot product of the reflected wave vector and that vector r, which is equal to the dot product of the transmitted wave vector and that vector r. We can make use of the identity that the vector r can be written as minus the cross product of the normal with the cross product of the normal and that vector r. We then derive the following relation: that the cross product of the incident wave vector with the normal is equal to the cross product of the reflected wave vector with the normal, which is equal to the cross product of the transmitted wave vector with the normal. Since the cross product of the incident wave vector and the normal point perpendicular to the plane of incidence, both the cross products of the reflected and transmitted wave with the normal must also point in the same direction. The only way this can be is if the incident, reflected, and transmitted waves are coplanar. Now the angles are all defined by expressions of the form of the dot product of the wave vector with the normal. So in the case of the incident wave vector, we have the magnitude of the incident wave vector times cosine of the angle of incidence, and a similar expression for the transmitted wave vector. Now for the reflected wave vector, notice we have a sign on front because the reflected wave vector is traveling in a leftwards direction. So it's minus magnitude of the reflected wave vector times cosine angle of reflection. If we take magnitude of the cross products on the left, we'll get magnitude of the incident wave vector times sine of the angle of incidence is equal to the magnitude of the reflected wave vector times sine of the angle of reflection, which is equal to the magnitude of the transmitted wave vector times sine of the angle of transmission. The dispersion relations are all of the form K is equal to index of refraction times frequency over the speed of light. Both the reflected wave vector and incident wave vectors propagate through the same medium, which is characterized by an index of refraction n1. So therefore, the magnitude of the reflected and incident wave vectors are equal. It then follows from our cosine relations that the angle of reflection is equal to the angle of incidence. And finally, if we plug in the dispersion relations into our sine equations, we can derive Snell's law. The index of refraction of medium 1 times sine of the angle of incidence is equal to the index of refraction of medium 2 times sine of the angle of transmission.
Here we see depicted the three fundamental laws of geometric optics. The incident, reflected, and transmitted waves are coplanar, and the normal also lies in this plane. The angle of reflection equals the angle of incidence, and we see Snell's law. In this simulation, it's been assumed that the index of refraction n2 is greater than the index of refraction n1. This is why the transmitted wave vector is bent towards the normal rather than away from it. In this next simulation, the index of refraction n1 is greater than the index of refraction n2. This is why the transmitted wave vector is bent away from the normal rather than towards it. Our next task is to relate the electric field vectors and magnetic field vectors of the reflected and transmitted waves to those of the incident wave. The most general kind of plane wave can be broken into two kinds of waves: perpendicular polarized waves, also known as S-polarized waves, and parallel polarized waves, also known as P-polarized. The letter S stands for the German word senkrecht, which means perpendicular, and the letter P stands for parallel. The terms perpendicular and parallel refer to the orientation of the electric field with respect to the plane of incidence. For S polarized waves, the electric field is perpendicular to the plane of incidence, and for P polarized waves, the electric field is parallel to the plane of incidence.
We first consider the special case of normal incidence, which corresponds to an angle of incidence 0 degrees. For normal incidence, there is no distinction between polarization. Remember, the plane of incidence is defined by the cross product of the incident wave vector and the normal to the interface. For normal incidence, both of these vectors point in the same direction, and hence their cross product is 0. Therefore, the plane of incidence is undefined for normal incidence. And as a consequence, there is no distinction between polarization. The Fresnel coefficients for normal incidence are, for the reflected wave, n1 minus n2 over n1 plus n2, and for the transmitted wave, 2n1 over n1 plus n2. Once the electric field is determined, the magnetic field can be found from the following relation. Index of refraction over c is equal to times the cross product of the direction of the wave vector and the electric field. Conversely, the electric field can be found from minus c over n, cross product of the wave vector direction and the magnetic field.
In this simulation, in all similar simulations, purple arrows represent electric field vectors and green arrows represent magnetic field vectors. If n1 is larger than n2, then the electric field of the reflected wave is in phase with the electric field of the incident wave. The electric field of the transmitted wave is always in phase with the electric field of the incident wave. Because the three vectors k, e, and b form a right-handed orthogonal set, the direction of the magnetic field can be determined. From this viewpoint, if the incident electric field points up, then the incident magnetic field points out of the screen. Likewise for the transmitted wave. However, the magnetic field of the reflected wave points into the screen. If n2 is larger than n1, then the electric field of the reflected wave is 180 degrees out of phase with respect to the electric field of the incident wave. The magnetic field of the reflected wave now points out of the screen. Transmitted wave is, of course, in phase with the incident wave.
We now turn our attention to oblique incidence. We'll consider perpendicular or S polarization first. Perpendicular polarization means that the electric field is perpendicular to the plane of incidence. These are the Fresnel coefficients for the reflected wave and the transmitted wave. For the reflected wave, we have n1 cosine theta I minus n2 cosine theta t all over n1 cosine theta I plus n2 cosine theta t. For the transmitted wave, we have 2n1 cosine theta I all over n1 cosine theta I plus n2 cosine theta t. The Fresnel coefficients relate the reflected wave, reflected electric field to the incident electric field, and the transmitted electric field to the incident electric field.
This is a plot of the Fresnel coefficients for normal incidence to grazing incidence for linear media characterized by indices of refraction n1 equal to 1 and n2 equal to 1.5. Yellow represents the transmission coefficient for perpendicular polarization, and red represents the reflection coefficient. As we just noted, the transmission coefficient is always positive and goes to 0 as grazing incidence is approached. However, the reflection coefficient is negative over this range and approaches -1 as grazing incidence is approached. Note that some authors plot the absolute value of the coefficient of reflection. Here the index of refraction of the second medium is now 15. We see the same kind of qualitative behavior as in the previous simulation, only the profiles are flatter with the coefficient of reflection quite close to -1 across the range and the coefficient of transmission smaller. Here's how the electric and magnetic fields of the incident, reflected, and transmitted waves behave for n2 greater than n1. Once again, purple arrows represent electric field vectors and green arrows represent magnetic field vectors. We have assumed perpendicular polarization, so the incident electric field is perpendicular to the plane of incidence. From this viewpoint, it points out of the screen. Given that the incident wave is perpendicular polarized, we determine the relations between the electric fields of reflected and transmitted waves from the Fresnel coefficients. There are only two possible directions for the reflected and transmitted electric field vectors. They're either in the same direction or in the opposite direction. Because the transmission coefficient is positive, it follows that the electric field vector also points out of the screen. Because the reflection coefficient is negative, it follows that the electric field vector for the reflected wave points into the screen. The incident electric field vector is known, then both the magnitude and direction of each magnetic field can be determined. Notice further when the angle of incidence approaches 0 degrees, we'll regain the simpler formula for the Fresnel coefficients.
We'll next consider parallel polarization. This means that the electric field vectors lie in the plane of incidence and the magnetic field vectors are perpendicular to this plane. The Fresnel coefficients for p polarization are given by reflected wave n2 cosine theta I minus n1 cosine theta t all over n2 cosine theta I plus n1 cosine theta t. For the transmitted coefficient, 2n1 cosine theta I all over n2 cosine theta I plus n1 cosine theta t. Unlike the Fresnel coefficients for perpendicular polarization, the Fresnel coefficients for parallel polarization are relations between magnitudes of the reflected and transmitted electric fields and the incident electric field. There is thus ambiguity in the definition of these coefficients. Some authors of electromagnetism and optics books write the coefficient of reflection as they are written here. Others, including Griffiths, transpose the terms in the numerator. Although there is ambiguity in the definition of the Fresnel coefficients for parallel polarization, there is no ambiguity in the direction of the fields of the waves themselves. For along the way to deriving the Fresnel coefficients for parallel polarization, we derived expressions relating the transmitted and reflected magnetic fields to the incident magnetic field. The reflection coefficient is identical, and the transmission coefficient is identical except for a factor of n2 over n1. Watch the corresponding lectures for a more detailed explanation.
Fresnel coefficients for parallel polarization with indices of refraction n1 equal to 1 and n2 equal to 1.5 are plotted. Here light blue represents the coefficient of transmission and green represents the coefficient of reflection. Notice that while the coefficient of transmission is positive over the entire range, the coefficient of reflection takes on both positive and negative values. Remember, there's ambiguity in the Fresnel coefficients, so some authors plot the coefficient of reflection as the negative of what is plotted here. At one special angle of incidence, the coefficient of reflection vanishes. This is Brewster's angle. If we increase the index of refraction of the second medium to 15, we'll see the same kind of qualitative behavior as in the previous simulation, except that the reflection coefficient takes on overall larger values than the transmission coefficient, and Brewster's angle is closer to 90 degrees. Let's consider the behavior of the electric and magnetic fields of the incident, reflected, and transmitted waves for an angle of incidence less than Brewster's angle. Because we consider here parallel polarization, the three magnetic field vectors will be perpendicular to the plane of incidence. For this angle, both reflected and transmitted magnetic field are in phase with the incident magnetic field, and all three vectors point out of the screen from this viewpoint. Knowing the directions of the magnetic fields and the directions of the wave vectors, we can determine the directions of the electric fields. The Fresnel coefficients only give the relations between the magnitudes of the electric fields of the reflected and transmitted waves and the incident wave, which is why we have to take this additional step in our analysis. Let's look at what happens when the angle of incidence equals Brewster's angle. For this one angle, there is no reflected wave, only a transmitted wave. There is a Brewster's angle for parallel polarization, but there wasn't one for perpendicular polarization. For non-magnetic media, the cases we're investigating here, there is no Brewster's angle for perpendicular polarization. However, Brewster's angle is possible for combinations of certain types of magnetic materials.
Brewster's angle is found from Brewster's law. Tangent theta b, where theta b is Brewster's angle, is equal to n2 over n1.
The angle of incidence is greater than Brewster's angle, then the magnetic field of the reflected wave points in the opposite direction from the incident and transmitted fields. In this viewpoint, the magnetic field of the reflected wave points into the screen and the electric field vector is altered accordingly.
We conclude this discussion of an electromagnetic wave propagating across an interface from one linear medium to another linear medium of higher refractive index with an analysis of reflectance and transmittance defined as follows. The reflectance is equal to the square of the Fresnel coefficient, and this holds for both S polarization and P polarization. The transmittance is equal to N2 cosine theta t over N1 cosine theta I times the square of the Fresnel coefficient for transmission.
Here we see the reflectance and transmitted plotted for both perpendicular polarization and parallel polarization. The indices of refraction for the two media are 1 and 15, respectively. Light green and light blue represent, respectively, the transmittance and reflectance for the perpendicular polarized wave. Notice that they are mirror images of each other and that the transmittance goes to 0 at grazing incidence, while the reflectance goes to 1. Pink and dark blue represent, respectively, the transmittance and reflectance for the parallel polarized wave. Again, note that they are mirror images of each other. This is why you usually just see a plot of the reflectance and not the transmittance. The reflectance is 0 at Brewster's angle, and the transmittance is 1 there. Also, the transmittance goes to 0 at grazing incidence, while the reflectance goes to 1. Let's consider what happens when an electromagnetic wave is incident on an interface going from a medium of higher index of refraction to one of lower. In other words, N1 is greater than N2. Recall that the transmitted wave bends away from the normal. As the angle of incidence increases, eventually the angle of the transmitted wave will approach 90 degrees. From this angle of incidence and beyond, the wave will be totally reflected, and consequently, there will be no transmitted wave. This is the critical angle. The dashed line represents the critical angle, and in this simulation, the angle of incidence is greater than the critical angle. The incident wave is totally reflected, and this effect can be observed when you are underwater and look up at the surface.
The critical angle can be found from the following expression. Sine theta c, critical angle, is equal to N2 over N1.
This is a plot of the Fresnel coefficients for perpendicular polarization for N1 equal to 1.5 and N2 equal to 1. Yellow represents the coefficient of transmission and red represents the coefficient of reflection. Both coefficients are positive up to the critical angle. Beyond this angle, Snell's law gives complex angles. As the critical angle is approached, the coefficient of reflection approaches 1 and the coefficient of transmission approaches 2. The directions of the electric and magnetic fields can be determined as before. This is a plot of the Fresnel coefficients for parallel polarization, again for N1 equal to 1.5 and N2 equal to 1. Light blue represents the coefficient of transmission, and green represents the coefficient of reflection. The coefficient of transmission is positive over the range from normal incidence to critical angle, but the coefficient of reflection is negative and then becomes positive. The coefficient of reflection is 0 at Brewster's angle. As the critical angle is approached, the coefficient of reflection approaches 1, and the coefficient of transmission approaches 2 N1 over N2. Final plot is of the reflectances and transmittances for both kinds of waves with indices of refraction 1.5 and 1. As a critical angle is approached, the reflectances approach 1 and the transmittances approach 0. One other angle where the reflectance for parallel polarization is 0 occurs at Brewster's angle.